Welcome to The Explainer. Right off the bat, I want you to imagine we're stepping into a high-tech, holographic physics laboratory together. We are about to explore one of the absolute most fascinating frontiers in science, quantum mechanics. Specifically, we're going to look at the behavior of electrons, not as tiny, solid spheres, but as matter waves. We want to see what actually happens when we try to force these waves into a confined space. So, how exactly do you trap something that's both a particle and a wave? That is the core puzzle we are tackling today. Think about it. If an electron behaves like a wave, it has a wavelength, a frequency, and it inherently spreads out over space. So how do you put a wave in a box? And more importantly, what happens to that wave when you actually manage to lock it up? Well, the answers completely rewrite the rules of classical physics, and they actually form the foundation of everything from modern electronics to the structure of the universe itself.
Okay, let's dive into this. Part 1. Trapping a matter wave.
To really understand this, let's attempt to build a theoretical cage for an electron. We'll start with the simplest possible trap, just a one-dimensional tube with infinitely strong walls. Now this brings us to a foundational rule called the confinement principle. Basically, when you physically confine a matter wave, you force it into quantization. This means the electron literally cannot just have any random amount of energy anymore. It can only exist in specific, discrete states with very specific, discrete energy levels. It's kind of like a standing wave on a guitar string that's pinned down tightly at both ends. That string can only vibrate in specific patterns, right? Half a wavelength, a full wavelength, 1.5 wavelengths, and so on. The electron's matter wave works exactly the same way between the rigid boundaries of our trap.
Notice the aggressive contrast here between the physics you experience every day and the weirdness of the quantum realm. A classical particle, like say a marble trapped in a tube, can roll back and forth at any speed. It can have absolutely any continuous value of kinetic energy. But our quantum wave? It is completely restricted, because the wave must fit perfectly between the walls of our trap. With fixed nodes at the boundaries where the wave's amplitude is strictly zero, only certain specific energy states are mathematically allowed to exist.
The absolute lowest possible state the electron can occupy is designated by the quantum number n equals 1. In classical physics, our marble could just sit perfectly still in the tube, possessing zero kinetic energy. But in quantum physics, n cannot equal 0. A confined particle must always possess a minimum amount of energy, which we call zero-point energy. Because it is a trapped wave, it is literally never ever perfectly at rest.
All right, moving on to part 2, escaping the finite well.
Of course, an infinitely strong trap is just a mathematical construct. If we move our holographic simulation a bit closer to reality and make the walls finite, well, things get weird. But before we look at a realistic trap, we need to know how to actually read our instruments. We can't see a wave function directly in the physical world. Instead, we use something called the probability density. Mathematically, it's the absolute value of the wave function squared. Basically, if we stick a probe into our trap, this density tells us the exact likelihood of our electron materializing at that specific point on our digital readout.
Now, what's really interesting about this is an incredible quantum surprise. In our theoretical infinite well, the probability density hits exactly 0 at the rigid walls. The electron absolutely cannot exist there. But in a finite well, like a real-world trap, the matter wave actually penetrates into the solid walls. Classical Newtonian physics says an electron absolutely cannot exist inside this barrier. And yet, our readings show the matter wave leaking into a space it mathematically shouldn't be able to enter. No way, right?
So, because the matter wave leaks into the walls, it effectively stretches out. This gives the electron a longer de Broglie wavelength compared to an infinite trap of the exact same size. And because the wavelength is longer, the allowed quantized energy states are actually lower. Furthermore, if we pump enough energy into our finite trap, the electron's energy will eventually exceed the depth of the well. Once that happens, its energy is no longer quantized at all. It breaks free of the confinement entirely and just becomes a free particle.
Part 3, 2D corrals and 3D boxes.
So far, we've only trapped our electron on a single one-dimensional line. Now let's scale up our lab's displays and add some more dimensions. Scientists actually build these multidimensional cages in the real world. They create artificial traps using structures called nanocrystallites and quantum dots to literally confine single electrons. As a crazy example, scientists at the University of Washington actually managed to hold a single electron in an artificial trap for months on end. By keeping it caged in these microscopic corrals, they were able to measure its precise properties with staggering accuracy.
Let's move to and see how this builds mathematically as we add physical dimensions. In a 1D tube, the energy is defined by a single quantum number, n. If we upgrade to a 2D rectangular corral, the matter wave has to fit into both the length and the width perfectly, so we get two quantum number readouts on our heads-up display, nx and ny. Jump to a 3D box, and the wave must fit into 3 dimensions simultaneously, quantized by nx, ny, and nz. Every dimension we add simply requires another quantum number to define exactly how the matter wave fits inside the trap.
Which brings us to Part 4, Nature's Trap, Hydrogen.
We've built artificial traps, sure, but nature has already perfected the ultimate 3D wave trap, the hydrogen atom. For a long time, the classical Bohr model taught us to view the atom like a tiny solar system, with solid electrons circling the central proton in neat little orbits. But quantum mechanics reveals a much stranger reality. Through the lens of the Schrödinger wave equation, the electron isn't a planet at all. It's a matter wave trapped in a complex potential well, where the depth of the well constantly varies with the radial distance from the nucleus.
Because the hydrogen atom is a complex 3D trap, Schrödinger's equation generates 3 essential readouts, or quantum numbers, to precisely define the state of the trapped electron. You have the principal quantum number n, which determines the energy of the state. The orbital quantum number L dictates the magnitude of the angular momentum, and the magnetic quantum number ML tells us the orientation of that angular momentum in space. Together, these 3 numbers define exactly what the trapped wave is doing, the whole shebang.
And finally, Part 5, the fuzzy quantum ball.
Okay, now for the ultimate visual payoff. We have the math and the quantum numbers, so let's translate these probabilities into physical, glowing shapes. To map the atom, we use a concept called radial probability density. Imagine drawing 2 incredibly thin, invisible spheres right around the nucleus, one just slightly larger than the other. The radial probability density tells us the exact mathematical likelihood that our electron will be detected somewhere in the space between those 2 shells. We are moving from pure math to mapping a physical location probability.
And this brilliantly illustrates the reality of nature's trap. This is the ground state of hydrogen, n equals 1. It is not a flat ring or a neat orbit. It is a spherically symmetric, fuzzy ball of probability density. The density of those tiny dots represents where the electron is most likely to be found. It actually drops exponentially as you move away from the center, peaking right at what we call the Bohr radius.
But watch what happens when we inject energy into the atom. The electron is forced into higher quantum states, n equals 2, and so on. The simple fuzzy sphere completely transforms into these visually stunning, neon-glowing probability clouds. Because the orbital and magnetic quantum numbers shift, the wave creates intricate, symmetrical geometries. You get these lobes and rings of probability where the electron is allowed to exist, separated by nodes where the probability is absolutely strictly 0.
This is the true architecture of matter. By understanding how a wave acts when it's confined, we unlock the exact structure of the atom itself. Everything you touch, the screen you are watching right now, the chair you are sitting in, absolutely none of it is made of tiny solid spheres orbiting like planets. It is all constructed from these quantized, fuzzy probability clouds, buzzing with zero-point energy, constantly leaking into the spaces around them. Will you ever look at the physical, solid world around you the same way again? Thank you so much for joining me on this explainer, and keep exploring.